Dependent samples. The methods up to this point within this module have dealt with comparing two populations, and the samples from the two populations, we're assuming that they are independent. Well, it's often the case that the samples are actually not independent, but in some sense they are paired, and we motivated that on the first page of this module by saying that a dependent samples approach can help eliminate extraneous factors or confounding factors. And so if you can use a dependent samples approach, then try to use it. And here's the first technique within that we're going to consider. I want us to first look at an example to give us a sense of kind of the structure. So I'm skipping ahead here to an example. Take a moment, read this example, hit the pause button. Okay, so what we have here are some pain measurements before and after hypnotism. And so the question is, does hypnotism, does it have an effect on lowering pain? And if you look at the sample, the way it's set up here is that the same person had their pain measurement was taken twice. It was taken before hypnotism and after. And so to assume that this sample here is independent of this sample here, that these two rows are independent of each other, they're samples, that would not be valid, because those are, the data is paired here, and so they're dependent on each other. And so what's actually done is we look at the difference of the data, and I'm going to come back to this in a little bit. We look at DI, which is the difference of the data. Okay, so with that in mind, let's come back to the beginning discussion here. When testing two populations from dependent samples, we actually analyze, I just said this, the differenced data. We let D be y1 minus y2, and mu sub D is the difference of the two population means. And this effectively takes us from from two samples down to one sample. And so then we can use techniques from the previous module that dealt with inference on a single population mean. Okay, so but just to be complete, we'll go through a whole problem under this dependent samples paradigm. So if you're in the dependent samples paradigm and you want to check to see if mu1 is less than mu2, that's a left tail test on the mean difference being, or the mean difference being negative. That's the alternative hypothesis. If you want to check to see is mu1 different than mu2, that's the same as checking to see if the mean difference is not 0. And lastly here, if you want to check if mu1 is bigger than mu2, that's equivalent to checking if the mean difference is positive. Okay, so all of these hypotheses here, left tail, right tail, two-tailed, can still be done, and it's not too surprising here. So again, we take the differences in our data, and in doing so we're ready to do our analysis. The assumptions here are that the distribution of the D's are normal, or that the number of pairs is large, and then we also assume that both samples are random samples. Okay, and these assumptions in tandem are equivalent to an assumption of the t-test on a single population mean, or a z-test on a single population mean if the sample sizes are large. Okay. With these assumptions, we can test these kinds of hypotheses. Now, we can test here, is the mean difference large? Okay, here I'm looking at the right tail test. Is the mean difference large? Is it bigger than D naught? D naught's a specified value. Typically it's chosen to be 0. It doesn't have to be though. It could be something other than 0. To check to see if the mean difference is larger than some specified value there. So we'd have a right tail test, left tail test, two tail test on the mean difference. The test statistic here, it looks like the one sample t-test. Just to kind of refresh your memory, remember the one sample t-test looks something like this. Okay, and this is actually the same test, except instead of having X, I've got D, because I'm dealing with the differences here. Okay, just to be clear, D bar is the sample difference, so it's the sum of the DI's divided by N. D naught is the mean difference under the null hypothesis. SD is the standard deviation of the differences given by the formula here. Okay, and then of course there's the sample size. The degrees of freedom with this particular distribution here, this particular t-test, is n minus 1. And so actually let me write that out here. I want to make that complete. The test statistic for this test is given by T, which has a degrees, which, let me insert here, which follows a student's T distribution with degrees of freedom n minus 1, and again here where the standard deviation of the differences is given by that formula. Now, if the sample sizes are large, or if the number of pairs is large, then you can use the you can use the standard normal distribution as your test statistic. Okay, the confidence interval for the mean difference is given by this formula here, and if you look at it, it looks a lot like the T interval that we had for a single population mean, which was this expression there. Again here, if you want to, if n is large, if the number of pairs is large, you can replace the T with a Z. Okay. Alright, so actually I'll leave that there. Let's go on to an example. Back to the example rather. Okay, so pain measurement are taken here. Pain measurements are taken before and after hypnotism. Does it work? Alright, so here's some data. This is actually a fictitious data set, as I recall. I don't think it's real data, but as my memory serves, it's a fictitious data. I don't have a reference for it. But I'm sure this sort of thing has been done. The difference for subject A, I'm going to take 6.6 and subtract 6.8, and if I do that, I would get negative 0.2. Then I would take 6.5 minus 2.4, and I would get 4.1. The difference associated with subject C is 1.6, with D 1.8, with E 3.2, with F 2, with G 2.9, and with H 3.6. Okay, and so I've got these differences here, and really my parameter of interest now is involving the differences. I'm interested not in two means here, but really just mu sub D. Mu sub D is the population mean difference. The population mean difference in pain measurements before and after hypnotism. Okay, and the hypotheses here, again, look for the claim that we're going to test. That goes in the alternative hypothesis. I would specify that first. Here's HA. The question is, does hypnotism appear to be effective in reducing pain? So is the mean difference, I'm sorry, that's not right. Is the mean difference positive? That would correspond to the before being greater than the after on the average, or is the mean difference positive there? Okay, is there a reduction in the pain? Okay, so the null hypothesis then would be that mu d is less than or equal to 0. Okay, so really all you would do here is now you do a t-test, t-test on the differences. It's that straightforward. Okay, so hopefully you've done several t-tests from this in the single sample paradigm. And if you do that, I'm going to give you some of the oh, I have a whole page here. I didn't know I had a whole page. Okay, I'm going to give you some of the statistics from this. So if you want to first compute d bar, you would add those up. Add up the differences, divide by n. So you'd have negative 0.2 plus 4.1 plus dot 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 plus 3.6. All that divided by, let's see, how big is our sample size? Is 8. And so if you did that, you should get a sample mean difference of 2.375. Okay. Clearly the sample mean is bigger than 0. But we're asking the question, is the margin by which it's bigger than 0, is that margin large enough to conclude that the population mean is also 0? Okay, so the hypothesis test is trying to answer that question. The standard deviation of the differences here, you recall the formula for that. Actually, let me write out the variance here first. It is the deviations of the differences. You add those up, divide by n minus 1. That gives you that variance there. And so what you want to do here is you'll first have negative 0.2 minus 2.375 squared plus dot dot dot. Do that through all of the measurements. Lastly, you'll have 3.6 minus 2.375 squared. Divide that by 8 minus 1, or 7, and if you do that, then you should get here, 1 point or close to 1.876. Okay, and so what that means then is the standard deviation is the square root there of that value, which is 1.3698. Or if you want to write it, I guess we maybe should write it as 1.370, or 7 rather. That's my d bar. SD, the t statistic here. The t statistic, my observed t statistic, is 2.375 minus d naught. That's the value of d under the null hypothesis. I've got a, whoa. See if I can get this straight. I've got a right tail test, looks like this. My D naught is 0. Alright, so I have a 0 here, and 1.37 divided by the square root of 8. If you do that computation, you will get a t statistic of 4.9, which is really a large test statistic. I mean, if you want to, you could set up the rejection region here if you wanted to set it up. Here's my rejection region. It's a right tail test, so I'm going to look at t sub alpha. And here in this case, what's alpha? I can't remember. Alpha is 0.01, so I'm going to look up t sub 0.01 on the t distribution table. And that's the value of t such that the area under the curve to the right is 0.01. And here I'm actually looking on a book here, t sub 0.01. The degrees of freedom is 8 minus 1, or 7. I have 7 degrees of freedom. And the t value is 2.998. So anything to the right of this is my rejection region. Okay? And so what's the decision? So clearly our test statistic falls. Let's see here if we can write. It's not really want to pick that up, is it? Our test statistic falls in the rejection region, so we would reject the null and accept the alternative. So in terms of a decision, so because our observed test statistic lies in the rejection region, we reject H naught and accept HA. The interpretation here what does this mean? Well, that what it's saying here, the interpretation, okay, mu d is bigger than 0. The average difference in pain measurements was reduced. I'm sorry, the average difference in pain measurements was positive, and so on the average, pain was reduced after hypnotism. So we have sufficient statistical evidence to conclude that the pain measurement in there, I'll let you fix that, the pain measurement is reduced on the average after hypnotism. Hypnotism. Spell that right. Okay, so that's our interpretation. If we want to do a 99% confidence interval, we certainly can. So we can do a 99% confidence interval for the mean difference. Again, the formula is similar to the t interval formula, d bar plus or minus t sub alpha over 2 with n minus 1 degrees of freedom. That's my t value there, times sd over the square root of n. So if I would just plug in the values here, we saw earlier that d bar was 2.375 plus or minus the t value. Okay, so if you look up here, I'm going to need a t sub 0.01 over 2 or t sub 0.005 value. You look that up in your table, you should get 3.499. Okay, so that's my T percentile, 3.499. The standard deviation, again, was 1.3798, or I'm sorry, 1.37. Is that what we had? Yeah, 1.37. And then divided by the square root of n, the square root of 8. You do the arithmetic here, you should get a confidence interval with a lower bound, roughly 0.68, upper bound 4.07. Okay, so if we interpreted this, we would have a statement that would say something like, we are 99% confident that the average difference is between 0.68 and 4.07, or that on the average hypnotism has a reduction in pain of at least 0.68 units, or at most 4.07 units. Okay, this is a paired t-test, or dependent samples t-test on population mean.